All right, Spartan fans, section 7.4, trig identities. Identities are a fancy way of saying that we're going to do proof. I think that you're going to find this to be a lot easier than the proof that you do in geometry honors, but it is proof nonetheless. So to begin, we're going to start with the primary identity, which says sine squared theta plus cosine squared theta equals 1. And there are several variations of this identity. You can subtract cosine squared from both sides. This is the difference of two squares. So you can also say that this is 1 plus cosine theta times 1 minus cosine theta. Along those same lines, you can say that cosine squared theta is 1 minus sine squared theta, which is the same thing as 1 plus sine, 1 minus sine. All right, along those same lines, you know that if you divide both sides by sine, the primary identity, you divide both sides by sine, you get 1 plus cotangent squared theta is equal to cosecant squared theta. Okay, you can also then say that 1 is equal to cosecant squared minus cotangent squared, and you can probably see where I'm going with this. Difference of two squares, cosecant plus cotangent, cosecant minus cotangent. All right. You can also, instead of subtracting cotangent from both sides, you can subtract 1 from both sides. And you can say that the cotangent squared of theta is cosecant squared minus 1. These are all variations on the primary identity. I'm just doing some addition, some subtraction, and then doing some factoring. Cosecant squared minus 1 is the same as cosecant plus 1 times cosecant minus 1. Why am I doing all this? Because all of these variations in some way, shape, or form are probably going to come up in a proof. And it's going to make things a lot easier for me to prove if I can substitute some of these identities. You take the primary and you divide by cosine squared. You get 1 plus tangent squared is equal to secant squared. Again, a variation. Divide sine squared plus cosine squared equals 1. Divide everything by cosine squared. And that gives you 1 plus tangent squared is secant squared. Okay, subtract tangent squared from both sides. Again, difference of two squares. Secant plus tangent, don't say tan. Please don't say tan. Tan is not a mathematical term. So I subtracted tangent from both sides. I could also subtract 1 from both sides and say tangent squared theta is secant squared minus 1. Secant plus 1, secant minus 1. That's a lot, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? There's 15 variations. There's probably more, and I probably miscounted. There you go. Okay, who cares? So what? We're going to be doing a lot of substituting when we start doing our first identity. Here we go. Definitely going to use my erasable pens. So there are a lot of rules with identities. The first is you cannot add and subtract from both sides. So what do I mean by that? Okay, let's say you have something like cosecant to the fourth theta minus cosecant squared theta is equal to cotangent to the fourth theta plus cotangent squared theta. Okay. You cannot subtract cotangent to the fourth theta from both sides. This is not an algebra equation. You're not trying to solve for the cotangent or the cosecant or whatever it is. Moving functions back and forth is not allowed. When you move functions back and forth, you're assuming it is true. You don't know it's true yet. You have to prove. So when you are doing an identity, you are always only allowed to work on one side. May only work on one side. You may only work on one side. Okay, choose a side. I don't know why generically we choose the left side to work on. So I want to take these cosecants and I need to somehow turn them into cotangents. Well, if you look, I have an identity that involves cosecants and cotangents. It is likely that you are going to make a mistake and you are going to need to erase. I may make a mistake when I'm doing this. We shall see. I want cosecants. I want to take them out and I want them to become cotangents. Okay, so I know that cosecant squared is 1 plus cotangent squared. All right, that's one way to go about it. So I could do a substitution of 1 plus cotangent squared is equal to cosecant squared. Now, you're not going to write these steps along the way. When you're doing the actual proof, you're just going to do, boom, 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 boom. I'll show you what I mean. So this is one option. I could take out the secant squared and put in 1 plus cotangent squared. But what about cosecant to the fourth? Okay. I look at this and I say, this is the difference of two squares. Factoring never leaves you. I'm going to go the factoring route and see what happens. So this factors as cosecant squared minus 1 times cosecant squared plus 1. That equals cotangent to the fourth plus cotangent squared. And you know what? I made a mistake. I don't like this. How about we just factor out? That's much easier. Why don't we just factor out a GCF of cosecant squared? Let's just factor out a cosecant squared. Cosecant squared is 1 plus cotangent squared. I did a substitution. Cosecant squared is, where is it? 1 plus cotangent squared. So I took that out. I'm going to do another substitution. Cosecant squared minus 1. Cosecant squared minus 1 is cotangent squared. Now, why am I not using cosecant plus 1, cosecant minus 1? Because I'm headed towards cotangent to the fourth plus cotangent squared. I want to get rid of the cosecants. So cosecant squared minus 1 is cotangent squared. I'm just rewriting the right-hand side. This is not acceptable. You are not done. You are not done until the left side matches the right side. This does not match. You need to do the distributing. So when you distribute cotangent squared, you do get cotangent to the fourth theta plus cotangent squared theta, and that equals cotangent to the fourth theta plus cotangent squared theta. There are several ways to do identities. In the big picture, this way is the fastest. You can do whatever way you want, as long as there's no voodoo math along the way. There is the first proof of the section. Is it okay if you would have written it as cotangent squared theta plus cotangent to the fourth theta? Of course, they don't have to be like identical, but you do need to do the last step here of the distributing. Let's take a look at, how about, again, proof. Let's do 1 minus sine squared over 1 minus cosine is equal to negative cosine of theta. Let me How do you know where to start? That's always the biggest question. I have this complex, I've got a fraction, this, this whole, whatever you call it, expression. It's going to be much easier to whittle this down into one term than it is to take negative cosine and expand it out. First thing, and you cannot, so for example, the denominator is 1 minus cosine theta. You cannot multiply both sides by 1 minus cosine theta. That is not allowed. You may work on one side and one side only. So what I'm going to do is find a common denominator. You do not need to write off to the side what I'm doing. You don't need to write down that you're finding the common denominator. I'm only going to look at your actual math. So the common denominator is 1 minus cosine. Okay, and combine the two fractions. This becomes 1 minus cosine minus sine squared all over 1 minus cosine. Notice I have not touched the right-hand side. Do not cross off the 1 minus cosines. That's voodoo math. You cannot cross off the 1 minus cosines. You have a binomial in the denominator. The only way that you are going to take a binomial, 1 minus cosine, and get it down to a monomial is to factor and reduce. You will get better at this. I'm going to show an extra step. This is 1 minus sine squared minus cosine over 1 minus cosine. All I did was reorder the terms, so you can skip that step. Okay, 1 minus sine squared. 1 minus sine squared is 1 minus sine squared, cosine squared. Do a substitution. As you get better at this, do you see it? Some of you maybe will already see what's coming up and how we're going to get there. It's close. But binomial, binomial, I need to get that down to a monomial. The only way that's going to happen is to factor and reduce. So I'm going to factor out a cosine in the numerator. That leaves me with cosine theta minus 1 over 1 minus cosine theta. There you go. Cosine theta minus 1, 1 minus cosine theta, these reduce to negative 1. And you indeed do get negative cosine theta equals negative cosine theta. You don't have to put the check mark. I put the check mark because it makes me a sense of satisfaction when I actually did it right. And do 2 more. Practice, practice, practice. How about the cosecant of u minus the cotangent of u is equal to the sine of u over 1 plus the cosine of u. When all else fails, if it's got a secant, a cosecant, a tangent, whatever, rewrite the functions using sine and cosine. That's generally a good place to start. So cosecant is 1 over sine. Cotangent is cosine over sine. Sometimes I get lazy and I just draw an arrow, and that's okay if you do that. Great. So I get 1 minus cosine u over sine u, and that's equal to blah, blah, blah. Okay, so we're going to cheat legally. Many times I see students just flip the fraction over magically and they get sine u over 1 plus cosine u. No, 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 no. I know what I want this expression to equal. I want it to equal sine over 1 plus cosine. So what I'm going to do is I'm going to legally cheat. And I want to get to a 1 plus cosine u in the denominator. So I'm going to multiply the numerator and the denominator by 1 plus cosine u. I would not know to do this if I didn't know where I was headed. Yes, you're allowed to do this. 1 plus cosine over 1 plus cosine is just 1. You're allowed to multiply by 1. So now in the numerator, 1 plus cosine, 1 minus cosine, 1 plus cosine, 1 minus cosine, sine squared. Do you see it? Sine 1 plus cosine. I just rewrote this sine times 1 plus cosine. Sine squared in the numerator, sine in the denominator, reduce. Sine squared in the numerator, sine in the denominator, reduce. And you are indeed left with the sine of u over 1 plus the cosine of u. I apologize that the writing is so light, but I kind of need to do erasable pen for these in case I totally mess it up. Practice, practice, practice. How did I know to multiply? Because I knew that was what I needed to get to. I needed to get to 1 plus cosine u in the denominator. Why didn't I multiply by, there's a sine in the numerator. Why didn't I multiply by sine over sine? You can try it, but it takes some extra steps. It's okay if you want to try multiplying by sine over sine. Doesn't help you as much. One more. Practice, practice, practice. All right, I'm gonna go for it. Non-erasable pen. Oh, I think I'm gonna regret this. Okay, the problem I'm using from the book says V. I don't like V. I'm gonna use theta. I just don't like writing it, frankly. So I'll focus the camera in just a second. Okay, cosecant minus 1 over cosecant plus 1 is equal to 1 minus sine over 1 plus sine. Okay, let me try it. Okay, it's not super great. When all else fails, start by writing in terms of sines and cosines. Cosecant, 1 over sine. I already know I'm going to need a common denominator. So rather than writing 1 over sine minus 1, I'm going to write 1 over sine minus sine over sine. The denominator, 1 over sine plus sine over sine. Do not, under any circumstances, reduce any of this. You can't go randomly crossing off sine over sine. No, 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 no. Okay, well, this is 1 minus sine. The numerator is 1 minus sine over sine. The denominator is 1 plus sine over sine. Do you see it yet? Such a great feeling when I see it. There it is. Complex fraction, denominators are the same. 1 minus sine over 1 plus sine. Not so bad. Your last step should show that they are the same. I love putting the check. And there you have it. Try, try, try. Do not give up. You're not going to get better at them unless you actually make some mistakes along the way. Trig identities. We'll do some more in the next video.